All right, welcome everyone. Welcome to the May Gen 3 Community Forum. I'm Michael Fitzsimons, Director of Research Programs and Outreach for CTDS. I'm excited about today's community forum. It occurred to some of us recently that there's very different ways that different projects have approached data analysis and data exploration, and we hadn't really brought a bunch of groups together to kind of share how they're doing this. So this is not in any way meant to be exhaustive, but hopefully it gives you a little bit of taste today of a few different approaches. So next slide, please, Faye. So we have I think a pretty interesting panel today. First, we have two speaker sets from CTDS. So we're gonna hear first about the Biodata Catalyst project and their use of the portable format for biomedical data. Later, the other CTDS topic is about task execution service. Oh, sorry, just back up a second, Faye. Can you go back one slide, Faye? Oh, there we go. But second, we're going to hear from Rance Nelt of the Michigan State University to hear about their Tox Data Commons. And then finally, to round out the program, we're going to hear from Jingsu of Indiana University on AI Ready Data Commons. So before I kick off the first talk, Bob, did you have any other opening remarks you wanted to make?
No, I just want to welcome everyone and to everyone in the audience. If you would like to give a talk or if you have suggestions for future community forums, please send them our way to Michael Fitzsimon or Michael Fitzsimon and myself. We're very much like to hear you speak and hear your ideas for future community forums. Back to you, Michael.
Great. So with that, I'll turn it over to our first speaker, Kyle Burton.
Hey, good afternoon, everyone. My name is Kyle Burton. I'm a lead software engineer at CTDS, and I'm also the technical lead for Biodata Catalyst powered by Gen3. Today, I wanted to talk through how we use PFBs and the new Gen3 user data library in Biodata Catalyst, and how we use that to host and export multimodal data from Gen3 to Terra in the Seven Bridges system. Can we go to the next slide? So just some background on Biodata Catalyst. It is an effort launched by the National Heart, Lung, and Blood Institute. It was launched in 2018, and it is a cloud-based ecosystem that we work with several different partners external to CTDS. The two of relevance today are Terra and Valsera, but we also work with another group called Picture outside of Harvard. Now, our role, Gen3's role in this ecosystem is to provide APIs for data queries and downloads. These APIs are used by Terra and Valsera's analysis platforms to provide workspaces filled with a rich set of tools and resources for their researchers to do research activities using data that is coming from Gen3. Can I go to the next slide? So the way that we interoperate with Terra and Valsera is using PFBs. PFB stands for the portable format for bioinformatics. And the reason we really like PFB is that it allows users to transfer data, the data model, and the pointer to files all in one package. So, you have your BAM and your CRAM files, you have tabular clinical data about participants in various studies and other metadata around those files. And you also have a data model that describes, what all of that means. another reason we like it is because while that data can be transferred, it keeps the data in its original structure. And there are three parts that make it up. One is the schema, which kind of describes all the columns in that CSV, the metadata, which describes how those columns link to each other. So you can think of it of, if you have clinical information tied to a subject, that describes how, your clinical data will link back to that subject. And then you actually have the data, which is, the rows in that CSV. Could we go to the next slide? So to give you some background on how we use PFBs in BDC, historically, PFBs were handed off from our Gen3 exploration page. Now, for those who don't know, this is the cohort builder that Gen3 offers. So researchers can come in here. There are a variety of different search facets that they can select a cohort from. And then when they export to Seven Bridges or Terra, the PFB is generated and it contains all the information for any subjects that match their search facets. And it also includes pretty much everything in the data model that is of relevance to those subjects. Could we go to the next slide, please? So some past observations that we had with this approach is anytime a user comes in and they want to generate a PFB, it's done dynamically, takes some time and it takes some compute. And what we've noticed is that most researchers that we work with on BDC prefer handing off the entire study or data sets at once, and then they kind of sort through that data on their own. Another opportunity that we've noticed is whenever we have data sets that come in with new different types of data. So, BDC is primarily associated with clinical data, clinical and genomic data. But when we get things that are imaging or sleep study or any other type of data that doesn't really fit to our data model, we have to expand our data dictionary to include these new types of data. This takes time, and there's like a lot of back and forth that we have to go through. And our discovery page, which we'll get into in a second, that on BDC provides a source of truth for our data set level metadata. So dbGaP study registration information, some FHIR data, and then DOIs are all associated through our discovery page. It's easy for researchers to search there, but there isn't really a good way to select data sets that you find relevant through the discovery page. And previously, there was no way to actually do a handoff from discovery to our analysis platforms. So as I have here at the bottom, if we could figure out a way to grab these three observations, we can make things much easier for researchers to find data that they're interested in and get it into an analysis platform. And we would also reduce the amount of friction that our data ingestion team has when new types of data come into the system. Could we go to the next slide, please? So the idea that we came up with on BDC is this concept that we like to call whole study PFBs. So our BDC data ingestion pipeline will create a PFB for each study in BDC. These are accessible through the Gen3 discovery and the Gen3 user data library, which I will get into in a second. These whole study PFBs contain data for the entire study. We create them at two parts during our data ingestion process. When we get the files from our data submitter, which for BDC is the data management core. So we'll get the files from them. We'll create a PFB encapsulating those files. Those are put on the discovery page. And then once that data set is harmonized to the BDC data dictionary, we will create another PFB representing that harmonized data. The second point is the most interesting one, which is these whole study PFBs can use a data dictionary that is independent of the deployed Gen3 Commons data dictionary. So currently on BDC, things are harmonized to our deployed data dictionary for BDC, but there is no restriction for us to use a data dictionary that is different from that, which is really, really nice. It makes us a lot more flexible. And the thing I like the most about them is they are available for transfer immediately. There's no need to wait for the PFB to be dynamically generated and handed off. Can we go to the next slide? So this is our Gen 3 discovery page, how it's represented in BDC. A quick note, I'll use the term study and data set interchangeably, but what I mean when I say either one of those words is in BDC, we separate our data sets by study and consent. So, you know, the Framingham study has 2 consent groups. They're authorized separately, and as a result, the data sets, we keep them separated. So even though both of these consents are probably considered the same study, you will hear me use these terms interchangeably. So just a little note there. But these whole study PFBs, we make them available on our Gen 3 discovery page. Users can select these data sets and they can add them to lists to their data library. And like I said before, the Gen 3 discovery page also contains a bunch of other rich publicly available metadata, kind of describing what these actual data sets are. Can I go to the next slide? So, like I said, we put these PFBs in our discovery page, and they're, you know, users go to discovery, they select data sets that they find interesting, and then they add them to their data library. So what is the data library? Well, the data library is a new addition to the Gen 3 product stack that we've been working on for the past year. And its main goal is to provide users the ability to create and manage lists of data sets. In BDC, these lists will contain whole study PFBs that are from that discovery page that I mentioned earlier. These lists are persisted across sessions, so researchers can always reference the data sets that they used in their analysis. And list items can be handed off to analysis platforms. So we'll go through that in a second, but in BDC, these are the Broad's Terra system and the Volsera 7 Bridges system. In Gen 3.2, we're planning to have support, you know, to hand off later this year. And it is extendable to any analysis platform or workspace that supports PFB parsing. I know that there are efforts to have PFB introduced as a standard to GA4GH. So we're really excited as that effort continues, but it will allow us to interoperate with any analysis platform that does support this PFB standard. Going on to the next slide. So this is a little overview of how this analysis handoff works. So users will export whole study PFBs to either one of analysis systems, where these analysis systems will open the PFBs up, they will parse them and organize the data into data frames. The files that are within these PFBs are still accessible through GA4GH NERSC. Those are also pulled into their workspaces. So Terra and 7 Bridges, they both have a nice, huge suite of tools for working with BAM, CRAM, all these different types of files that we have in our system. So, you know, those get parsed out, and then, you know, those systems can go through and provide various tools for researchers to interact with those files. You can kind of see this interaction here. So a user selects the destination that they want this PFB to go to, and then as it moves over, it gets parsed out and you know, displayed to the user. We go to the next slide. So just to summarize a lot of the benefits to this approach is these PFBs are available for transfer immediately. There's no need to dynamically generate the PFB, and this reduces not only the time that researchers wait to get things into analysis, but it also cuts down on our compute costs because we're no longer generating these PFBs, every single time somebody wants to export them. We've also noticed just through talking with users that they'll start an export, they'll go to a different tab, but they'll start working on something else. They'll come back and they'll have to relog in and regenerate that PFB, just session timeouts. This also reduces data model constraints on data ingestion, which is what I mentioned earlier. We have not taken full advantage of this on BDC yet, but I'm hoping that, as we move along over the next year, that we'll start taking advantage of this feature. And because there is no data model constraint, there's support for other types of data before the data model adjustments. So, data can be harmonized to other Gen3 data dictionaries. So if we get an imaging study, that maybe it's better to use Midrix data dictionary for that rather than BDC's data dictionary. This gives us support for doing things like that in the future. And again, data can be made available much sooner. Data submitters can provide their own Gen3 data dictionary, and as long as the data they give us conforms to that data dictionary, PFBs can be generated and hosted on our discovery page and available for handoff instantly. And then there's better data provenance and easier versioning and archiving in the future. This is a use case that we run into quite a lot on BDC, whereas new studies are updated, consent groups change between study versions. So, as previous versions of studies get replaced with newer versions, those whole study PFBs can be archived and kind of kept in the background, just as a historical record. And again, I just want to reiterate, this gives us a lot more flexibility to support different data types, going forward. And then finally, I believe this is my last slide, just some quick links and documentation. So the Gen3 user data library is the backend service that handles the API and authorization for those lists. The Gen3 front-end framework provides the user interface for the data library along with, the Gen3 Data Commons. PyPFB is the tool that we use to create whole study PFBs in BDC. It's available through the Gen3 SDK. So, we recommend using the Gen3 SDK PFBs commands to create PFBs whenever possible. And if you want to learn more about how PFBs look in BDC, Biodata Catalyst has a Git book with a whole host of documentation there. Do we have any questions?
Maybe we have time for one question, if there's any. We can also do questions at the end too.
Well, I have one comment, but I want to make sure if anybody had questions.
Go ahead, Kyle.
Yeah, I was wondering, we're very excited about the PFB standard. But I think we've actually logged a couple of issues. We tried using PFB to convert some more advanced data schema. So we tried moving fire data into PFB and noted a couple of issues related to limitations within the schema. They're in the issues for PyPFB. And I'm just wondering if you guys had a chance to review those yet. And if there's any thoughts about additional enhancements to the PFB standard before it became ratified as something like the GA4GH standard.
I can cover part of that discussion, and we can also take it offline. But we have seen the issues. I did respond, I think, that we were wondering how much of it, we could collaborate on. I guess if that's something that you can create a PR or yeah, how we can kind of work together on that particular update. Bob, did you have more to say about the GA4GH standard generally, though?
It's a priority for us to be able to accept data models like FHIR and others. So if you could help us with that, that would be great. And if other people want to propose other formats, this is focused a bit on Gen3 right now, but the Gen3 data models, but we want to be as agnostic as possible. So Kyle, please help us get the pull request. looking forward to working with you on it.
Yeah, I linked to the specific issues. We had some generalized suggested enhancements. We could try to work with you to develop those into full pull requests. So
Thanks.
That'd be great.
All right, I think we should keep moving since we're running a little behind schedule. But thanks a lot, Kyle Burton, for the presentation, which gives hopefully some people might not have known about those different front end features or the PFB stuff before. So next on the docket is Rance Nault from Michigan State University, who's going to talk about enabling collaborative environmental health research using the Tox Data Commons. So take it away, Rance.
All right, perfect. Thank you. If we can go to the next slide, although I think it's the same. Yeah, so I'm excited to be on this side of the community forum. So my name is Rance Nault. I'm an assistant professor at Michigan State University in the Department of Pharmacology and Toxicology and the Institute for Integrative Toxicology. And this will really focus on the work that we've been doing developing and using Tox Data Commons to analyze environmental health science data. So next slide. Thank you. So since it's sort of the first time that I think I talked to this group, I wanted to sort of introduce how we got to Gen3 Data Commons and why it's serving our purpose. So what our Gen3 Commons is basically used for is for this MSU Superfund Research Center. And it is the goal of Superfund is to essentially provide practical scientific solutions to protect health, environment, and communities. I mean, it's based on all these Superfund sites that were sort of all over the US that were basically result of a lot of sort of environmental contamination and highly polluted sites. And so it's this highly collaborative effort that includes everything from biomedical research to training students to environmental engineering and community engagement and data science. So it's a really multifaceted, group effort. And specifically, our Superfund Center looks specifically at environmental contaminants that activate a receptor called the aryl hydrocarbon receptor, because those are of interest for communities in Michigan, especially. So if we can go to the next slide, please. So as we sort of renewed our Superfund Research Center, one of the things that was requested is that we have a data management analysis core whose objective was basically to manage and integrate all these data assets that are generated by all these different groups that are tackling these environmental health challenges. And so the goal was basically to foster the interoperability of the data across all our centers, projects, and cores, which was a pretty huge ask. And so we're working with a lot of different types of data, different sources of data, different data streams. And so when we sort of embarked on this journey, we've looked at, okay, well, what are the options for us to actually tackle this? So if we can go to the next slide. So first of all, what we did is we looked at what is the current status of environmental health science sort of data set sharing. Because we knew from our field and from the work that we've done before is that there's thousands of data sets that are available through public databases and repositories. This is just a very short list of these, and some of them are very focused on environmental health science, so SEBS, which is the chemical effects in biological systems, and some of these you probably or might have recognized, just Data Dryad, Figshare, which is more of these generalist repositories, and Gene Expression Omnibus is overall gene expression. And we, when we were looking at this, these repositories, we were looking at, well, are these going to essentially address the sort of challenge that was put forth to us in terms of managing all these different data sets and making them interoperable so we can really gain new knowledge from all the data that we generate. So, the new term that was sort of put forth is this fair, findable, accessible, interoperable, and reusable. And do these databases actually meet those criteria? So if we can go to the next slide. So what we did is we went in some of these databases and we looked at, do we have enough metadata in any of these to even be able to do anything with them? And what was really fascinating is and this is specifically focused on database in the gene expression omnibus, which is probably one of the most mature repositories out there that has a lot of environmental health science data. And through sort of kind of manual looking, we were able to find about 1,200 data sets that are relevant to environmental health sciences. And what we did is we asked, based on metadata that we would expect for studies that are toxicology or environmental health, how many of these are actually reporting enough metadata that we can actually reuse them? And so I've highlighted in this red box, this line, which is 25%. And in this yellow box are where things start to kind of fall below 25% of the data sets reporting this. And as you can maybe see, I know the text is a little bit small, but within those boxes are time point, dose, and how compound was administered. All things that are super critical to understand what those data sets are. So we have less than a quarter of the data sets reporting this, which makes it incredibly challenging. And so we already knew that we were facing a challenge right away. So if we can go to the next slide. So that led us to develop the Tox Data Commons, because one of the things we really liked about the Gen3 Commons is the fact that the data model is there and that it can handle a lot of different data types, and we can actually kind of customize it for what we need. So we were basically motivated by this massive gap in environmental health science data to sort of address that problem. And Gen3, yeah, ended up being, what almost looks like a perfect solution as we were developing this. So this is our Tox Data Commons, just kind of a quick overview of kind of the top of it. And so you've probably seen a lot of pages that look like this. It's a pretty standard template. And if we can go to the next slide. What I want to, previous slide. I just highlight one specific part. So here I highlight example analyses. And so the reason I highlight this is because what I wanted to focus on for this presentation is kind of the analysis that we do with using Gen3. And as part of our training, what we've been able to take advantage of is this example analysis and applying that. So if we can go to the next slide. So to do that, what we did is we developed a couple of use cases. And these use cases are examples of some collaborative research between projects. So this is different labs generating independent studies. And I'm going to emphasize two of them. I will say, so our data commons is very early stage. So we're just starting to get data in there, which I'll touch on a little bit. But the way that we develop this is through those example analyses. We're developing these Jupyter notebooks that can then be used by students, even other researchers, as kind of a training example in how to use this data, but also show some actual useful applications. And the way we then use these is through our in-house high-performance computing cluster, because we have access to numerous different tools, even for artificial intelligence, machine learning, and compute and everything we need to be able to deal with this. So we have kind of a simple example where we look at gross pathology, that's just like body weights and liver weights and things like that. And another where we just recently did with a AI graph neural network type of analysis. So we can go to the next slides. So the way that we accomplish this, I think is going to look familiar to a lot of you that have been working with Gen3. So we have a pretty standardized workflow. So we have a template-based submission system. Actually, we have been working pretty hard on a Google Sheets-based data submission system because we have so many different projects uploading data. And we needed to standardize that aspect. So that I won't touch too much on, but I think this is something really valuable that we've developed and our users seem to be okay with it and like it. But what we do from that is because we have all that metadata, well, then we can start building those cohorts and selecting those properties of, what is the samples that we want to include and what are the data sets that we want to include when we start doing this collaborative research. So do we want to have just all the data from males or all data from a specific rodent strain and those kinds of filter that we can apply. And we just use the Gen3 client as well as the Gen3 SDK to download these files based on the manifest.json files. We've also used the SDK as well to download not just the data sets that are associated with that cohort that we've essentially build out, but also to build out that metadata and connect that metadata that's really important for us to be able to understand what's going on with our actual data. So if you can go to the next slide. So I'm going to talk about a couple of cases. So our first case here is integrating gross pathology. So when I say gross pathology, I mean body weights and liver weights. And we're in here because we're talking about environmental contaminants and things like that. We're talking about rodent studies. So we can't do this with human subjects at all. Here I show a very small example. We have 3 data sets, independent studies where we measured several different endpoints. So body weights, pathology, gene expression. And as you can see, the study design is a little bit different from all of them. So we have different doses of chemicals, we have different time points, but we still want to know, well, what can we learn from integrating in all these data sets? Are there things that we can narrow down that we need to explore further? Can we find certain patterns about the toxicity that's occurring from these? So you can go to the next slide. So here what we did is we just looked at the body weight growth, so it's daily body weight. So through this dynamic time warping analysis, and if we do nothing to it, we can already see, so with the gray dots here, that there's a couple of really big clusters, and then there's some points that sort of fall away from everything else. So when we do this analysis, what we can then do, now having that metadata from the comments and from our data model, we can then integrate, okay, well, what was the sex and what was the dose for each of these samples? And we can start adding that metadata. And as you can see in this plot on the right, you can see, oh, well, all of a sudden, those are the males with the 30 microgram per kilogram dose that is separating. And actually, if we look along the y-axis, that tends to separate by treatment duration. And along the y, it tends to separate by sex. So the darker colors are male and the lighter colors are female. So we can actually start to learn some stuff from our data. And again, this is a very simple example of that. We go to the next slide. And on top of that, what we can do is we can incorporate relative liver weight and see the correlation with that. And so when we correlate those values with the relative liver weight or liver weight relative to body weight, we can see that that also correlates with that daily body weight growth. And now we can start to learn things like we can predict that relative liver weight based on the sex and the dose of the treatment and everything like that. Go to the next slide. So our second case is metabolic reaction graph neural network. So as we are working through the problems that we can solve with all the data that we have, one thing that we often look at is metabolism. And that was particularly well suited for a graph neural network because metabolism is basically a network. And we had an example of sort of applying this. And so we got data from this Recount3, which just standardizes gene expression data, gene expression omnibus. And we were able to get, so we had about 4% of samples that we could use because so many were missing metadata, which is kind of pointing to the fact that we really need this metadata to be able to do this. But we were able to train a graph neural network model, which shows here sort of a good performance of that. And I'm going kind of superficial because it's just kind of an example application with a small number of samples here. But if we go to the next slides, what we can see is that we can then incorporate gene expression data that is in our data comments on that trained model. And we can start to classify, and here we show on the left how well our classification is, especially at those higher doses, like that 30 microgram per kilogram dose, as you can see at the top. So we can start to basically pull in our data from our data comments and run it through our graph neural network, and not only find the classification, but also find these reactions that seem to be central to certain toxicant exposure or contaminated exposure. So for example, this is one pathway called transfer of SUMO1, which is something that we didn't really find when we used more traditional methods, but we have seen in other more functional assays that is actually something that is affected. So we're able to pull out some of new information about some metabolic reactions that are affected. So we can go to the next slide. So I'll kind of summarize here. Gen3 I think really has been helping us sort of do these collaborations by kind of standardizing that workflow and allowing us to kind of pull in all these different data sets. So I talked about all these projects and cores that are generating data all independently. And we have that Google Sheets workflow where we pulled all that into our Tox Data Commons. And then we moved that data over to our high performance computing system where we run Jupyter notebooks and start analyzing that data. And we can kind of repeat as that data set and expands and as we add more in there. So really the key here was standardizing that metadata, which was a massive gap that we didn't have and was actually a big challenge for us beforehand. So we can go to the next slide. So just some future direction. So we're looking at containerizing some of these analyses, automating some of these multimodal AI ML tools to integrate all these different types of data, and also implementing some of these tools and resources in a more scalable manner for the whole center and hopefully expanding beyond the center. And right now, there's a lot of focus for us for getting these metadata collection tools, because that has been a pretty big hurdle for us to get data in there, which is why we're kind of low on data right now, but we're sort of building that out as well. So next slides. Yeah, so here I just want to thank everyone that's kind of helped us with this. What I want to highlight is massive amount of helps from the team at CTDS. Also, we're working with Crumware, who's helping us a lot, and a couple of funding sources as well. But I want to highlight that we're actually started working with another group looking at perivascular adipose tissue, who also want to copy what we've done for our Tox Data Commons for perivascular adipose tissue. And so we're working with them to develop that as well. So happy to take any questions.
Thanks a lot, Rance. I think we have time for one or maybe two quick questions.
Okay.
Feel free to unmute if you have any questions or type them in the chat. I guess I'll just say, Rance, it's great to hear more about what you've been working on, and it's kind of a good story. And yeah, looking forward to seeing what else comes out soon.
Yeah, we're excited, especially that now that we've got a lot of those little pieces figured out, especially the data submission and all that those analysis can really expand. So we've done sort of proof of principle that we can do it, but we're excited to kind of start dumping a lot more data in there and running all these analyses.
Yeah, great. Anything else from anyone? We can do questions at the end too.
Oh, I think I saw a question. Yeah, so is our I think your Google Sheet tool, is it available in a public repo? We're working on putting that into public repo. We're still evaluating a couple of things, but basically the way that it works is it essentially queries the comments directly and pulls in those templates, which has basically made it a lot easier for people to keep the identifiers along the way. But yeah, we're planning to put that public shortly.
Faye, can you go to the next slide then? Great, thanks, Rance. All right, so the next speakers are a duo from CTDS, Pauline and Artie, and they're going to talk about using the GA4GH task execution service in Gen3 for biological applications. Take it away, guys.
Hey, thank you, Michael. Hey, everybody, this is Aarti. I'm an assistant professor in the section of biomedical data science in the Department of Medicine at the University of Chicago, and I work at CTDS. Today, Pauline and myself are going to discuss the topic of how to run containerized workflows in Gen3 for biological research applications. So I'll start by outlining some typical use cases for biological research. So as a researcher, I'm interested in either developing a new workflow or running an existing bioinformatics or data science workflow for different use cases, such as RNA-seq analysis, variant calling, copy number inference, training or testing an AI/ML model, or even federated learning applications where data from multiple data commons could be analyzed separately results aggregated and post-processed in some fashion. Now, the workflows themselves could be written in popular workflow languages such as Nextflow, and the data for the compute could be either small scale, local data such as that used for testing and development efforts, or large scale data that lives remotely, example in an S3 bucket. In that case, I could either bring my own data or even analyze data from a data commons such as a Gen3 commons. Now, the workflow itself could utilize one or more containers for its task or processes. Now, for sequence analysis, typical containers like FastQC that perform base quality analysis, or Salmon for RNA-seq transcriptome quantification, Deep Variant for variant calling, and others are available as Docker containers from Docker Hub and other sources and could be employed in the workflow depending on the needs. Next slide, please. So we are building a mechanism to run such containerized workflows in Gen3 in a secure, isolated, and scalable manner. Now note that Gen3 is based upon Kubernetes and everything is container-based. So what we are doing here is adding a generic capability to run containerized workflows in Gen3. Next slide, please. So I want to provide a quick review of our previous proof of concept solution, which was a V1 solution, before handing over to Pauline for our current effort, which is V2. So in V1, we focused on running Nextflow workflows using the AWS batch backend. We implemented the security architecture, isolation, and hooks for Nextflow into Gen3 to run workflows in batch in a secure way. Now, Nextflow did not come with these settings out of the box, so we had to build the workspace and AWS batch VPCs, IAM policies, and integrate a pay model to enable all of this. Using this version 1 solution, a researcher can launch a Nextflow workflow simply from a Jupyter Lab notebook in the workspace using little to no specialized tools. Next slide, please. So in V1, here's an overview of steps that a researcher would need to do to run their Nextflow workflow. Some of these steps are also shared with our V2 solution that we are working on currently. Now, importantly, containers are run in a FedRAMP moderate environment with security compliance. So we built a process to security scan the user developed containers and give them approval to run their container in the workspace. So in step 1, a researcher would locally build and test the container using a Docker file, which is standard process. Step 2, they would request the credentials to push the container to a staging environment and get it approved, security approved. And once approved, the researcher would receive a container URI that they then plug into the Nextflow workflow to manually launch it from the Jupyter Lab notebook. So this V1 solution, we deployed it in the Biomedical Research Hub, which is one of the first data meshes that we built at CTDS. Next slide, please. So this is showing you a screenshot of how it worked. Is the researcher would select a pay model, a workspace image such as a CPU or GPU image according to the workflow needs, and run the workflow through a simple Python notebook and see the success or failure logs. Next slide, please. So this is an example of a screenshot where there is communication between Nextflow and AWS batch, and you'll be able to see the logs directly on your terminal. Next slide. Now this V1 solution that we had, previous slide, Faye. So the V1 solution that we had was good for low throughput development and testing efforts. It's limited to AWS batch and needed to have a pay model like direct pay integration. So our current focus, which is the next slide, Faye. Our current solution V2 is focused instead on programmatic submission of workflows using the TESS API. So this work is an active collaboration with Kyle Elrod's group at the Oregon Health and Science University and uses the funnel toolkit for distributed task execution. Thank you very much, Kyle, for making this available to us. Next slide. So I want to note one more thing before handing it over to Pauline to describe our V2 solution. In our V2 solution, the first 3 steps will be the same as that we use for V1. To run these containers in a FedRAMP environment, users will still need to get security scanning and approval of their containers. However, the final step of submission is different. Instead of manually launching them through the Jupyter Lab notebook, the difference will be that they can now launch it programmatically using the TESS API. So I'll now hand it over to Pauline to talk about the architecture for the TESS API integration, and also she'll show you a fresh out-of-the-oven workflow demo, which is one of our very first examples and early stage results. So Pauline, it's all yours now.
Thanks, Artie. Hi, I'm Pauline, a senior software engineer at the University of Chicago, working on the Gen3 software. So first, a little bit of architecture about how this is going to work. So from top to bottom, our user here has several options to run a workflow or run jobs in Gen3. The most straightforward option on the diagram is that they can interact directly with our TESS, GA4GH TESS API, or they can use a UI that we are planning to develop in the future, where they can, manage their tasks, see tests that are running, failed, succeeded, download their outputs, and see the Docker images that they have been approved to run. But here, I want to focus on the left part of the diagram, where a user wants to run a Nextflow workflow. So the user could use the Nextflow client directly on their computer, transparently. It makes no difference to them whether they're running their jobs, their workflow locally or in Gen3. So Nextflow allows you to choose between several backends to run your jobs. So here we would want to use the test backend. So we use the Nextflow test executor. What this executor does is translating a Nextflow workflow into a set of test tasks. So we configure this test executor to talk to the Gen3 workflow task API, to talk to our test endpoints. So on the Gen3 side, this API is pretty much just a wrapper around the funnel test API. So funnel is a tool for distributed task execution, developed and maintained by our friends at the Oregon Health and Science University, like Artie was saying. So the Gen3 API is a wrapper around the funnel API. It does a few things that we need on our side, like authentication and authorization of users. Okay, so as a user, you run a workflow. Nextflow sends the tasks to the test endpoints, which sends them to funnel. For each task, funnel creates a worker job, which itself creates a worker pod. This worker pod fetches the workflow inputs from S3, which here is what we use to share the inputs and outputs between the client and the backend. After fetching those inputs, the worker starts an executor job, which itself will create an executor pod. The worker pod and the executor pod both have access to the same EBS volume. So that's how they share access to the files. So the executor can access the files that have been downloaded by the worker pod from S3. It will run the task and then store the outputs. Then complete, terminate. The worker pod sees that the executor is done running. It fetches those outputs from the EBS volume, uploads them back to the S3 bucket, where Nextflow can download them and return them to the user. All right, next slide, please. So I want to briefly talk about two improvements that we're working on. The first one is that instead of using a single S3 bucket for the communication between the client and funnel, so funnel supports talking to a single S3 bucket, but we would like to have one bucket per user for better isolation. So each user has their own files in their own bucket. So what we did here is we implemented an S3 endpoint in the Gen3 workflow task API. what this endpoint does is it receives an S3 request. It resigns it with internal AWS credentials and then forwards it to S3. So what this achieves is that managing the AWS credentials and which bucket we want to talk to, that's done by the Gen3 API. The user, Nextflow, and the funnel worker do not need to know the details. All they have is a Gen3 access token that they send to the API, and then the API adds the AWS credentials we need and forwards that to S3. Next slide. All right, the second improvement we're making, it's pretty subtle on the diagram. Instead of running all those pods in the same Kubernetes namespace, we want to run them in two different namespaces. The first one is where the Gen3 system is running, all the services are running there, funnel runs there, and the workflow API runs there. And the second namespace is where we want to run the worker and executor pods and jobs. That allows us to have better isolation. So that's the second thing we're working on. Okay, next slide, and I will let you run the demo. This is a demo of the Nextflow and GA4GH test functionality in Gen3. So the first thing I want to show is hitting this endpoint of the Gen3 workflow API. When I hit this endpoint, the backend creates a bucket for my user and configures it. So as we can see on the left here, the bucket right now is empty. Here is the demo workflow that I'm going to show you. So this workflow has three defined steps. The first one is DICOM to PNG, that takes as input a DICOM file, converts it to a PNG image, and returns that as output. We're running it with two files, so it's going to run twice. There should be two tasks. The other two tasks are a Salmon demo. So Salmon is a tool for estimating transcript level abundance from RSNA-seq read data. In RSNA-seq, we routinely want to quantify transcript level abundances using a reference transcriptome. Salmon does this by creating an index from a transcriptome file in FASTA format. Once the index is computed, the transcript level abundances are quantified from the sample RSNA-seq reads file in the quant step. So here we have two input files for the quant step. The GUT1 and GUT2 files are RSNA read files sequenced from the GUT, used as input in our example to quantify abundances. So the Salmon index step outputs the Salmon index directory, which is used as input by the Salmon quant step. So the quant step depends on the index step. Here on the right, this is the same workflow, just in Nextflow language. So we have two input DICOM files that are the input to the DICOM to PNG step. And then we have our transcriptome file, the input to the Salmon index, which outputs the index directory. And then the Salmon quant step takes as input that index directory and the two GUT files here. Okay, so I also want to show briefly the Nextflow configuration. So here I'm telling Nextflow that I want to run this with GA4GH tests. I'm using two different images, so the DICOM step is using one image, and the two other steps are using a different image. I'm configuring tests to talk to the Gen3 workflow execution service. and I'm configuring Nextflow to use S3. The endpoint is again the workflow API, the Gen3 workflow API, and instead of configuring AWS access key and the secret key, I'm giving it a Gen3 access token. So the user will be authenticated by the API, and then that will be forwarded to S3. My working directory is the bucket that I was just showing you. So let's run this workflow. So here I'm running Nextflow. I'm also using a little Gen3 utility that sets up the access token for me. All right, so our 3 steps are here. If I have a look at the workflow API logs, I can tell that there's a lot going on here. I'm going to pause it just so I can show it. So there's a lot of requests that are coming from my user against that bucket. So the incoming request is what Nextflow is sending. The outgoing request is what the service is sending to AWS. Okay, so while I was explaining that, the workflow service sent some task creation calls to funnel. So right now I have 3 worker pods that are waiting to spin up. Not 4, because the Salmon quant step needs the Salmon index step to be done before it can start. Okay, so our 3 worker pods are running here. So if we have a quick look at the logs, we can see them downloading the input from S3. So this is the transcriptome input file being downloaded. Once it's done downloading, it starts the executor. So here we have 3 pending executor pods, 3 running worker pods. If I have a quick look at the jobs, we can see them here. On top are the 3 executors, and here are the 3 worker jobs. So while this starts, if I describe one of the executors, we can see that it's using the image that I have configured right here. Oops, yeah, this one. If we have a quick look at the Gen3 workflow logs, we can see that the Nextflow client is regularly hitting this get test task endpoint to monitor and see when the tasks are done. Okay, so 2 of the executors are running. Let's look at the logs for one of them. Okay, so this one is done. The second one is done as well, so that's our 2 DICOM to PNG. So we can see here that the Nextflow client is reporting that those 2 steps are done, and it's still waiting on the Salmon index one. Okay, here it started. Let's have a look. Completed the step.
Pauline, do you want to try to sum
The
up?
worker is still running. It hasn't seen yet that the executor is done.
Okay,
Oh, there you go.
this is the
Executor,
recording.
exit code. It's uploading the
I-
outputs.
Can we just sum up?
Faye, can you pause the video, I guess? We can share this with the community for review offline. I think Pauline and Artie, is there a summary you can add at the end? We're just making sure that we have enough time for the last speaker.
Yeah, I mean, I can just provide a quick few sentence summary in that we are working on providing many different types of examples, different types of workflows on various inputs and outputs, and we'll keep you all updated as we make more progress. I think we just had one slide after this with an overall summary, but we can end here if you're running
This
behind.
is a demo.
Yeah, this is the last slide.
Why don't you take a minute to go over the last slide?
Sure, yeah. So our current efforts, we are working on demo use case for different types of workflows, as I was mentioning before, working on tracking the compute costs for each user. And essentially the summary of this effort is that this will enable us to scalably submit workflows using the test API and compute over a large set of files in a scalable manner. So that's the overall summary in a nutshell, and we'll keep you all updated as we make more progress here. Thank you.
All right, thanks a lot, Pauline and Artie. I think just to make sure that we have enough time for the last speaker, we'll hold any additional questions on this for the end. But also thanks to the OHSU team who's listening in. I see. Sorry, I'm getting some requests in Zoom. Okay, Jing-Su, welcome. I'm turning over to you to tell us about your AI-ready data commons.
Thanks a lot. Can you see my screen?
Yes.
Okay, wonderful. Thanks a lot for this opportunity to present. My talk is on toward an AI-ready data commons from computable data centers to interoperable AI models. And first of all is some self-introductions. My name is Jing-Su, Associate Professor at the Biostatistics and Health Data Science Department in Indiana University School of Medicine. I'm the PI of the Biomedical Informatics Lab of about 10 members. Also, I serve as the Director for Data Management and the Service Team at the Biostats, and Associate Director of Real World Data at the IU Cancer Center. So a little bit introduction to the Data Management and Service Team. It has over 30 members. Supporting now more than 200 the projects with an annual budget over 3 million and supporting the research use of data across global, national, and regional research consortiums and networks. And one strategic focus of this of my team is to provide AI-ready data infrastructure and implementation. So it's a part of this work. So first of all, we all know that we see the new norm of complex data in clinical studies. Modern clinical studies often involve the real-world data components, including EMR, medical claims, clinical research data, multi-omics data, medical imaging and pathological imaging data, clinical notes and other free texts, and also data from various sources and programs. And it is challenging to make such data ready for machine learning or AI, and for such complex and heterogeneous data. I listed some typical examples, such as the Oncology Research Information Exchange Network, or RAN, the Alcoholic Hepatitis Network, which is called ALCAPNet, or all of us. They all share, they all provide great examples of such complex data. The solution will be using graph data model, graph artificial intelligence, and incorporate with a AI-ready research data commons to address such needs. So I guess everyone here are very familiar with the graph data models used widely by NCI-GDC as its foundation of data model for Gen3. The major take-home information from such graph data model is that it allows us to capture data of different modalities, of different resources into the same data model and reflect their relationship across those different modalities. And the graph data model enables AI in research in many ways. First of all, it allows us to incorporate the common data elements and the graph ontology into the data harmonization. It defines the integration and harmonization of real-world data and research data, enable clinical study designs in data commons, support the AI and machine learning readiness for biomedical big data, and has been widely used in real-world data infrastructures. And it's many national research has been benefited so much from the Gen3 the data commons framework to build their own data commons using the graph AI graph data models. So I would like to show a few successful stories. One is the ICOR Research Data Commons, which is an AI machine learning ready platform for clinical trials and observational studies. This is one of the 4 cores of the AlgoHabNet National Consortium. We just got the renewal of this consortium. It's over $23 million of the total cost. So the readiness of this alcohol research data commons contributed a lot to the successful renewal of this data coordination center grant for this consortium. So this RDEC provides some essential functionalities for clinical studies, including building a research cohort, collect data set, and then provide a workspace to analyze the data. And the here is the overall architecture. I guess that everyone here are very familiar with the majority of the architecture. I want to focus a little bit on the left side. So on the phase 1 of the RDEC, we collect data from 2 different data coordinating centers. From the IU School of Medicine, we get the clinical data from clinical trials and observational studies. From the UMass data coordinating centers, we get the biospecimen data and the downstream generated multiplex and multi-omics data, and we harmonize it together into a AlgoHabNet data warehouse, and then massage the data according to the RDEC graph data model to allow data to be searchable and useful on the RDEC data commons. And then here is the interface of the RDEC. And on phase 2, we proposed and we are funded to build Energy, the AI machine learning analysis engine for the RDEC data commons. So you can see that there are multiple ways to communicate with Energy. One is through the from Portal through React to directly talk to Energy, and Energy can either talk to the Elasticsearch index data or the original database, or users can connect to Energy through their workspace and to call the AI and machine learning models. And we are embedding machine learning models and AI models and functionalities into Energy to provide real-time or near real-time data analysis and visualization on the portal. That help us to offload some computing intensive work into on the server side and only visualize results on the user side. And recently, we have already successfully implemented the large language model, currently the Llama 3, into Energy to provide the a chatbot support for users to explore data and to visualize data. And hopefully, we can release the functionality into RDEC within this year. And based on such data, we are able to do AI. So one example demonstrated here is called the trial view. It's published last year. This allow us to visualize the clinical trial trajectories, and in the heart of the trial view is a graph AI model that incorporates the baseline information, temporary trajectory into a graph AI represented latent space. And in the latent space, we can do clustering to group patients with similar clinical trajectories in a clinical trial together. And then we can visualize visualize patients with different trajectory patterns, as shown in figure B, and also review for each group of them what's their major progression patterns. For example, as demonstrated in the figure D, this group of patients, after they receive the treatment marked as green, many quickly develop the AKI, acute kidney injury, as labeled as pink, and they die or they all fail the trial. So there's one example to show that how we can incorporate graph AI-based trajectory analysis on an AI-ready data commons. And so I would like to switch gear to another project called the Indiana Precision Oncology Research Data Commons, IPO. So this allow us to incorporate the clinical genomics data collected from RAN into this cancer data commons, and then provide the data to researchers in Indiana for their analysis. And briefly speaking, we collect the patient information from their electronic medical records, collect their biospecimen, and do sequencing, and then collect the clinical biospecimen and sequencing data, incorporate them together into Indiana Precision Health Information Data Warehouse. Then we incorporate such data into the IPO common data model and provide the data for researchers' use. So I would like to mention briefly what's the difference between IPO and RDEC. For RDEC, we embedded the support of clinical trial design and clinical study design, so that the clinical trial and the clinical study observational study-based analysis and visualization can be made possible. In IPO, we modified the current data commons to allow us to record all clinical events as follow-ups. This allow us to dynamically and flexibly define the index date and the outcome events for survival analysis, which is crucial for cancer. So that's the novel part from the IPO. And then I would like to quickly introduce another program we are funded called GAIPO, Graph AI for Precision Oncology. It's a supplement award from our P33 Cancer Center Award. So the idea is that my team and our colleagues' team have been developing biomedical graph AI models for precision oncology. This is one example called the DPEN. We incorporated the EMR data with the clinically generated multi-omics data together and use graph AI to identify which patients may benefit or not benefit from the immuno checkpoint inhibitors therapies. And the idea is to use a graph AI model to capture the similarity among patients and then represent the patients into the latent space and then identify different subgroup of patients in the latent space that demonstrate different responses to immune therapy. So this one example. It incorporated the EMR data with multi-omics data. The next example is from my colleague's lab called the DGAS. It incorporated the data from the tissue level, the multi-omics data from tissue level and from single cell level, as long as their clinical outcomes to subgroup patients, subtype patients, and to predict which patient may respond to which therapy, and to provide mechanical, cellular and molecular level mechanisms for why those patients respond to the outcome differently. So this model incorporated the clinical data, the bulk data, and the single cell data together, and also using the latent representation and the graph AI to do the prediction. The next model is published from my group. It's incorporating the single cell spatial transcriptomics data with their associated multi-channel images to better analyze the data and to better understand the difference in cell identities and in spatial regions, and to understand the contribution of the spatial heterogeneity in the normal tissues function and in the diseases and the drug responses. So again, it incorporated data from two modalities, image data and transcriptomics data, and using graph to reflect their spatial the adjacency, and use a graph AI model to incorporate the two different modalities together into latent space, and then to do the data analysis in the latent space. Another example is the called DSTG. It's also published from my lab. It incorporated the spatial transcriptomic data with single cell RNA-seq data to deconvolute the spatial data for their cell compositions. Similar again, we represent the data from two different modalities into the latent space and incorporate them using graph. So graph AI-based latent space representation for the modeling. You can see all of these models share the same pattern, incorporate the data from different modalities, using graph to connect them, present them into latent space, then do the downstream analysis. So we propose that why not let develop a common graph AI model pipeline that captures all of the common parts, and to deliver such type of graph AI models to users who are using Gen3 based data commons. So we are funded by NCI to try our idea on the CCDI, the childhood cancer data infrastructures, especially for incorporating our graph AI models and similar graph AI models onto the childhood cancer clinical data commons C3D3, which is using Gen3 also. So our aims are, first of all, we collect the childhood cancer data, including their clinical data, imaging data, and omics data from IU Cancer Center, and to divide and implement our graph AI models onto those data, and to prove the concept that we can implement graph AI models of this type onto a Gen3 data commons built locally. And once it worked, then we will implement our developed graph AI model onto CCDS Gen3 data commons, and to deliver our models for the national use on the CCDI. So we incorporate the data from different cancer types, different sources, different type of data, including clinical data, omics data, and pathological imaging data. And we build a common framework to automatically collect and incorporate such data. And so for different data domain, we'll extract the data from different sources, and then we will build the graph AI approach to represent such multimodal data into the common into latent space, and then perform the analysis on the data represented in the latent space. So here is the basic framework of the GAIPO that cover all the graph AI models I mentioned, and cover many other data models available. And so we propose to provide the following functionalities onto the Gen3 system, including the incorporating the following data domains like pathological images, omics data, and clinical data. And most of those data models will be inherited from the current existing Gen3 data commons, and will provide a series of graph constructor to incorporate those data, and will incorporate a series of feature extractor or encoders like VGG 16 for the imaging data, and also with other feature extractors. And we will provide different graph layers to perform graph AI models, such as graph transformer, GCN, JT, JN, GraphSage, and so on. And then we provide a different hybridization method to incorporate data from different domains together and provide the downstream functionalities, including decoders for autoencoding, classifiers for classification problem, deep survival module for providing survival analysis, clustering for subtyping analysis. So we have already finished the one model that incorporates the clinical data, bulk omics data, and the single cell data together and implemented on Gen3. We are now moving the other one, the single cell spatial omics data graph AI model onto the Gen3. And hopefully by the end of this year, all this model will be disseminated on CCDI and can be made available for other Gen3 based data commons. So the conclusion is the graph common data models and the research data commons are revolutionizing the modern clinical research. It provides the foundation of clinical genomics. They provide foundation for the clinical genomics research data commons. It enable AI or machine learning ready collaborative research ecosystem. It provides national data hubs across projects and institutes. It will play as the nexus for research and collaboration and engines for novel research. And I would like to thanks to the development and the collaborators for our tech team and also for the GAPO team. And thanks.
Thanks so much, Jing. You have a lot of interesting things going on right now, that you're working on. I think we could maybe take one question for Jing, and then we'll open it up to questions for everyone. I'll ask a question, Jing. I think it was more towards the beginning. You were talking about Anagene. Just curious if there was more details about where that is or when something might be released, etc.
Could you repeat your question?
Oh,
Again,
just
please?
about the status for Anagene.
Yeah.
Just if you have any more to say about that. If not, that's fine.
Okay, so we have been building a new endpoint for Anagene, and hopefully the Anagene can be running on a standalone microservices, and so that we can use the GPU computing and the more high performance computing support Anagene because we need a near real-time responses to get the data back to the portal. And I think this may be hopefully be synergizing with what the Gen3 team and the Chicago University of Chicago team are doing. And I believe that many of your work are on the workspace for the work that need a long time processing and need to run pipelines. And the energy is more on the real-time data analysis. Yeah, and I hope that we can disseminate our developed tool back to Gen3 to see whether it will be helpful for other users who are interested in that, especially for the large language model part. It's quite we are moving on quite a while. Hopefully, we can deliver that one soon.
Cool, great, thanks. Well,
Sure.
yeah, we're already in touch, but yeah, let's stay in touch.
Yes.
Cool. All right, we have just a 3 minutes left, so that's time to open up for questions on any of the topics today from the audience.
So
there's some answers, Jing, to some of your question that earlier in the.
Yeah, I'm reading now.
Just
Thanks
read
a
through
lot.
them, I guess. Yeah.
Yeah.
not seeing any questions, so everything was totally clear to everybody, which is good. All right, here's a question. Oh. Okay, well, I'll just give some closing remarks and maybe a question will appear after that. So yeah, thanks again, everyone. We don't have, well, first of all, I had a suspicion that we'd hear 4 radically different ways that groups are approaching enabling data analysis, and I think that was borne out. So I think that's a testament to how Gen3 can be taken in different directions. So that's really great to hear these examples. As far as next meeting, we don't have a plan right now. So if you have a topic that you want to pitch, feel free to reach out to me. Otherwise, we'll come up with something and maybe reach out to the community to present, because it's super valuable to hear these other examples of how people are approaching this. So with that, last call for questions. Okay, I'll let you all go a minute early. Thanks, everyone. Yeah, I really appreciate it, speakers. And we'll post the video and slides soon. Bye, everyone.
Thanks, everybody.
Thank you.